Now let's look more into the meta-directing groups. So these are the polar substituents, where the polarity is pulling electron density away from the ring. The atoms that are directly bonded to the ring don't have any non-bonding electrons directly bonded to them or directly on them. So no non-bonding electrons on atom directly bonded to the ring. And these are all electron withdrawing groups. Or EWGs. When you have an electron withdrawing group, it doesn't stabilize any carbocation intermediate, but it destabilizes the carbocations that are formed when you do ortho or para substitution. So that's why these are meta-directing groups, because it would require even more energy for these groups to undergo a substitution reaction where another electrophile is added at the ortho or para location. So these electron withdrawing groups destabilize the carbocation intermediate during substitutions at ortho and para locations. So let's first look at what the carbocation intermediate looks like, what resonance is possible when we have a meta-directing group and we substitute at the meta location. So we're doing meta substitution. We have our benzene ring. And then let's add the nitro group. So this is the most deactivating group, the NO2 group. Now if we are adding, remember we're just going to keep a general electrophile because we're not really focused on what's adding, just how the electron withdrawing group impacts the mechanism. And then let's say we're adding the electrophile at the meta location. So we've added the electrophile here. Don't forget we have a hydrogen there. Then we've generated a carbocation at the other carbon where that pi bond was bonded. That ended up breaking. So now let's look at resonance structures. We can shift around pi electrons to form the different carbocations that we would expect from doing one of these types of reactions. I'm going to abbreviate to NO2 here. So here we've shifted the carbocation to that carbon. We can do the same thing here. We have a different location where the carbocation is, but you notice this nitrogen can't donate any electron density to the ring. So that doesn't have any stabilizing effect. The carbocations look very similar to when we just have an unsubstituted benzene that we're adding an electrophile to. Now I said that having the electron withdrawing group destabilizes the carbocation intermediate during substitutions at ortho and para locations. So let's look at what happens when we do have a para substitution. We'll use the same starting material, nitrobenzene. And then we will add the electrophile at the para location. All right, so we've generated the carbocation. We have our electrophile bonded at the para location. I always like to draw out the hydrogen once we bond the electrophile to keep in mind that this carbon is now an sp3 carbon, this one that's bonded in the ring. So that's why I always draw that hydrogen after we bond the electrophile. I'll have to redraw those bonds here. Okay. So we've generated the carbocation. Let's look at some resonance structures. We can shift the pi bond to change the location of the carbocation. And now the carbocation is at that carbon. Having the carbocation adjacent to the nitrogen that's positively charged is extra unstable. So overall, this carbocation intermediate is less stable than when we do the meta substitution, so the carbocations above. Let's draw the last resonance structure, and then we'll write in some notes to really put into words why this is extra unstable. So we can shift the pi bond, the bottom right, so that we have a new location of where the carbocation is for our last structure. Okay, so the first and last resonance structures at the para substitution are about equal energy. But this middle one, this is the key resonance structure that helps us understand why electron withdrawing groups are meta-directing and not ortho-para directing. And that's because we have a carbocation adjacent to electron withdrawing group. In this case, that's an N+. That's extra unstable. Than a typical carbocation. So this is even higher energy intermediate. And that's why electron withdrawing groups are meta-directing. The same structure is possible. Oops. So the same possible resonance structures would be presented if you do the substitution at the ortho location. And starting with an electron withdrawing group. So let's just do the same thing we did before, looking at a reaction coordinate diagram to compare the energetics of these two locations of substitution. So we have energy on the y-axis. We have reaction progress on the x-axis. We're starting with the same reagents in both cases, where we have electron withdrawing groups. And if we form the carbocation at meta substitution, now I'm going to scroll back up to these structures. At the meta substitution, we can move the location of the carbocation, but we don't have any extra unstable unstable resonance structure. When we do the substitution at the para or the ortho location, we have this middle, the one that I've drawn in the middle, that resonance contributor that's extra unstable because we have positively charged atoms directly adjacent to each other. So if we put, having trouble scrolling up, but if we put the carbocation for the meta substitution at this energy, then the carbocation intermediate for the ortho-para substitution would be at a higher energy. So if we require, let's say, this activation energy to get to the meta substitution, then we'd require even higher activation energy to get to the ortho-para substitution. So that's why when we have electron withdrawing groups, meta products are observed at a higher concentration than the ortho or para products.